February 24, 1944, Anzio beachhead, western Italy. The darkness offered no protection anymore. Hauptmann Erich Schneider adjusted his throat microphone as his Junkers Ju-88 bomber leveled off at 4,000 meters, approaching the Allied positions from the northeast. Behind him, 11 more aircraft maintained formation, engines synchronized to minimize detection. The night raids had been working. For 3 weeks, the Luftwaffe had hammered the trapped Allied forces with near impunity, using the darkness and their electronic jamming equipment to blind the American SCR-584 radars. The beachhead was contained, the Allies were bleeding, and tonight would be another demonstration of German tactical superiority. At precisely 2200 hours, Schneider's bombardier began his approach sequence. The target coordinates were locked in. The jamming equipment hummed steadily, drowning out any radar signals the Americans might attempt. Below, the beachhead was a constellation of fires and explosions from previous raids. Schneider allowed himself a brief moment of satisfaction. Then, the sky erupted. 4 American 90mm guns opened fire simultaneously, with a precision that defied every assumption about nighttime anti-aircraft combat. The shells appeared exactly where Schneider's bomber would be 3 seconds later. He threw the aircraft into a violent evasive maneuver, but the next salvo adjusted instantly, tracking his movements as if the gunners could see through the darkness itself. Within 90 seconds, 5 of the 12 Junkers were burning wreckage, falling toward the Mediterranean. The remaining aircraft scattered, breaking formation in desperate attempts to escape whatever had locked onto them. Schneider survived only because his wingman's exploding aircraft created a momentary blind spot. As he fled north toward Rome, his hands shaking on the controls, he transmitted an urgent message to Luftwaffe, Command. The Americans had deployed something new, something that made jamming irrelevant, darkness meaningless, and evasion nearly impossible. What Schneider could not know as he landed his damaged bomber at Ciampino airfield was that he had just encountered the final evolution of a technology that would render traditional air defense obsolete. The radar system that had tracked him through every evasive maneuver was not simply better than previous Allied equipment. It was fundamentally different, representing a revolution in automatic fire control that combined microwave precision, electronic computation, and cybernetic tracking into a weapon system so effective that German engineers would later conclude it alone justified Allied aerial supremacy. The story of the SCR-584 is not about a single invention or breakthrough. It is about how American engineers took British microwave radar technology, combined it with unprecedented electronic computation, and created a system so automated that barely trained crews could achieve hit rates that would have seemed impossible just 2 years earlier. It is about how the convergence of 3 separate technological revolutions, cavity magnetrons, analog computers, and automatic tracking systems, created a weapon that could predict the future position of an aircraft and place high explosive shells exactly where that aircraft would be 3 seconds later. Most critically, it is about how German technical intelligence identified this system, tested, captured examples, calculated its implications, and reported to Berlin that the electronic war was already lost. The mathematics were brutally clear. When radar could track automatically, when computers could calculate firing solutions continuously, and when proximity fuses could detonate shells without direct hits, the defensive advantage shifted so decisively that no amount of pilot skill or tactical innovation could compensate. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. September 1940, Washington, D.C. The Tizard Mission had arrived carrying Britain's most closely guarded secrets. Among the technologies the British scientists revealed to their stunned American counterparts was the cavity magnetron, a device that produced microwave radio energy at power levels American researchers had considered impossible. The immediate applications for radar were obvious. Microwave frequencies allowed far greater precision than the long-wave systems both nations currently deployed. But precision alone did not solve the fundamental problem of anti-aircraft fire control. Detecting aircraft was one thing, hitting them was entirely different. The challenge was mathematical and brutally unforgiving. an aircraft traveling at 400 kilometers per hour covered over 100 meters per second. Anti-aircraft shells took between 3 and 8 seconds to reach typical combat altitudes, during which time the target aircraft would move 300 to 800 meters. Calculating the required lead angle involved solving differential equations that accounted for shell velocity, air density, wind speed, powder temperature, the curvature of the shell's trajectory, and the predicted future position of a moving target whose course and speed were constantly changing. Before 1940, this calculation was performed by mechanical computers like the Sperry M4 Director. These devices used gears, cams, and complex mechanical linkages to solve the ballistics equations. They worked, but they were slow, required constant manual adjustment, and could not adapt quickly to rapidly maneuvering targets. Skilled operators could achieve acceptable results against straight-flying bombers, but the systems became increasingly ineffective as aircraft became faster and more agile. The fundamental problem was that mechanical computation could not keep pace with the rate at which targeting data changed during combat. By the time the M4 calculated a firing solution, the target had already moved, and the solution was obsolete. Operators compensated through experience and intuition, but this meant that accuracy depended entirely on individual skill. A novice crew might fire hundreds of rounds without a single hit. The SCR-584 radar, introduced in the late 1930s, improved the situation somewhat by providing more accurate range and bearing data than optical methods. But the radar's 1.5-meter wavelength limited angular resolution, and the system still required manual tracking. Operators watched a cathode ray tube display and continuously adjusted controls to keep the target centered. This worked adequately for straight-flying targets, but became nearly impossible when aircraft maneuvered violently or employed electronic countermeasures. In 1940, Vannevar Bush, heading the National Defense Research Committee, recognized that the anti-aircraft problem required a completely new approach. The microwave radar technology, revealed by the Tizard Mission, offered unprecedented precision, but someone needed to develop a system that could track targets automatically and compute firing solutions fast enough to guide guns in real time. Bush established 2 separate divisions to tackle the problem. The Microwave Committee, Section D1, would develop the radar. The Fire Control Division, Section D2, would create the computing and control systems. The Massachusetts Institute of Technology was selected to host the radiation laboratory, where the radar work would be concentrated. Bell Telephone Laboratories would handle the computing and fire control challenges. Both institutions began work with extraordinary urgency. By December 1940, the basic requirements were established. The radar needed to operate at approximately 10 centimeter wavelength to provide angular accuracy, measured in fractions of a degree rather than degrees. It needed automatic tracking capability, so the antenna would follow targets without continuous operator intervention. It needed to provide azimuth, elevation, and range data with sufficient precision to guide 90mm anti-aircraft guns. And it needed to do all of this while remaining mobile enough to accompany ground forces in combat. The MIT Radiation Laboratory, under Director Lee Dubridge, assembled a team of physicists and engineers from universities across America. Ivan Getting, a physics professor, led the fire control radar project. The initial challenge was adapting the British cavity magnetron for American production and developing the antenna and receiver systems that would turn raw microwave energy into usable tracking data. Getting's team decided to use conical scanning, a technique where the radar beam is tilted slightly off the antenna's central axis and then rotated rapidly. When the beam points directly at the target, the return signal strength remains constant throughout the rotation. When the antenna is slightly misaligned, the signal strength varies as the beam rotates, creating an error signal that indicates which direction the antenna should move to reacquire the target. This error signal could drive motors that automatically adjusted the antenna's position, creating a self-correcting tracking system that required no human intervention once the target was acquired. The approach was elegant but required unprecedented precision in mechanical and electrical engineering. The antenna mount needed motors powerful enough to move a 200-kilogram antenna rapidly while maintaining pointing accuracy measured in hundredths of a degree. The receiver circuits needed to detect and process signal variations occurring thousands of times per second. The servo control systems needed to respond instantly to error signals without oscillating or overshooting. By April 1941, Getting's team had a working prototype. To test the automatic tracking system, they mounted the radar outputs to a gun turret salvaged from a Boeing B-29 bomber, replacing the guns with a camera. A colleague flew his light aircraft around the test facility while the system tracked automatically and the camera recorded whether it stayed locked on target. On May 31, 1941, the test succeeded perfectly. The antenna tracked the aircraft smoothly through turns, climbs, and dives, maintaining lock without any operator input. The system could detect bomber-sized targets at 40 miles range and track them automatically within 18 miles. Angular accuracy was approximately 0.06 degrees, roughly 1 milliradian, for a target at 30,000 feet altitude and 5 miles horizontal distance. This accuracy translated to pointing precision within about 30 feet. This was revolutionary, but it still did not solve the complete fire control problem. The radar could track targets automatically and provide precise position data, but converting that data into gun pointing angles required solving the ballistics equations continuously in real time. That challenge fell to Bell Telephone Laboratories and a team led by David Parkinson. December 1940, Murray Hill, New Jersey. David Parkinson, a researcher in Bell Labs' switching systems department, was struggling with a recurring nightmare. For weeks, he had been thinking about the anti-aircraft problem, trying to imagine how electronic systems might solve the fire control equations fast enough to be useful in combat. The problem invaded his sleep. Then, one night, he dreamed he was in an anti-aircraft battery during an air raid. The guns were firing, but instead of mechanical gun directors, each gun had a device that looked like one of the potentiometer assemblies used in telephone switching equipment. In the dream, the guns tracked incoming aircraft with perfect precision, shells exploding exactly where they needed to be. Every target was hit. When Parkinson woke, the solution was obvious. Telephone switching systems used shaped potentiometers and precision amplifiers to control electrical signals with extreme accuracy. The same principles could solve ballistics equations by representing variables as voltages and performing calculations using analog electrical circuits rather than mechanical gears. Parkinson spent the next 2 weeks working with his supervisor, Clarence Lovell, drafting specifications for an electronic analog gun director. The device would accept electrical inputs representing target position, range, and angular rates from a radar system. It would use wire-wound potentiometers to perform multiplications, vacuum tube amplifiers to provide gain and isolation, and shaped cam followers to implement complex mathematical functions. The output would be electrical signals representing the required gun azimuth and elevation angles, which could drive motors on the gun mount directly. In November 1940, Bell Labs submitted a formal proposal to the National Defense Research Committee. The proposed director would calculate aircraft course and speed, shell velocities and fuse timing, powder temperatures, shell drift, and air density corrections. It would update firing solutions continuously, hundreds of times per second, maintaining accuracy even against rapidly maneuvering targets. Most remarkably, it could control 4 separate 90mm guns simultaneously, allowing a battery to concentrate fire on a single target or engage multiple threats independently. The proposal was approved in December 1940. Parkinson and Lovell, working under Edward Wente's direction, completed the initial design within months. A prototype designated T-10 was delivered to the Army in early December 1941, just days after the attack on Pearl Harbor. The Army immediately ordered several hundred units, recognizing that the electronic gun director might prove decisive in the coming conflict. The device they created was designated the M9 gun director. It weighed approximately 3,000 pounds and required its own trailer for transport. Inside were hundreds of precision potentiometers, dozens of vacuum tube amplifiers, servo motors, and complex mechanical assemblies. To observers, it looked more like telephone exchange equipment than military hardware. But its capabilities were extraordinary. Once connected to the SCR-584 radar, the M9 created a closed-loop fire control system that required minimal human intervention. The radar tracked targets automatically. The M9 calculated firing solutions continuously. The guns adjusted automatically to follow the computed aiming points. Human operators needed only to monitor system status and authorize firing. Even the decision to fire could be automated through simple range gates and safety interlocks. April 1, 1942, Fort Monroe, Virginia. The complete system, SCR-584 radar connected to M9 director controlling 4 90mm guns, was demonstrated for the first time in integrated operation. Military observers watched as the radar detected an aircraft at maximum range, switched from search mode to automatic tracking, and locked onto the target. The M9 began calculating firing solutions immediately. Within seconds, all 4 guns were pointing at empty sky ahead of the approaching aircraft. When the aircraft entered effective range, the guns opened fire in automatic sequence. The shells exploded in a pattern that bracketed the target aircraft's flight path with brutal efficiency. The demonstration proved that 3 separate technological revolutions, microwave radar, automatic tracking, and electronic analog computation, could be integrated into a weapon system that fundamentally changed anti-aircraft warfare. The Army placed a contract for over 1,200 complete systems the following day. But development was one thing. Production was entirely different. The SCR-584 required precision manufacturing on a scale that pushed American industry's capabilities. The 6-foot diameter antenna needed to maintain dimensional stability within thousandths of an inch, while rotating at 4 revolutions per minute in winds up to 60 miles per hour. The receiver circuits needed hundreds of precision vacuum tubes, each matched to tight specifications. The servo control systems required motors and feedback mechanisms machined to tolerances normally reserved for scientific instruments. Chrysler Corporation's Dodge division received the initial production contract. Engineers converted a floor of the main Dodge plant in Detroit into a specialized assembly line for radar production. The cavity magnetrons came from Raytheon, where Percy Spencer's manufacturing innovations had enabled mass production. Vacuum tubes came from multiple suppliers, all meeting specifications developed by the Radiation Laboratory. Precision components came from machine shops across the industrial Midwest. The entire system represented American industrial capacity applied to electronics manufacturing with unprecedented scale and intensity. The first production SCR-584 was delivered in May 1943. Chrysler quickly ramped production to several units per day, then dozens per week. By late 1943, the production line was delivering approximately 15 systems daily. Each complete unit included the radar set, the M9 director, power generators, and all necessary cables and accessories, packed in trailers that could be towed by standard Army vehicles. Testing revealed capabilities that exceeded the original specifications. The radar could detect aircraft at ranges exceeding 40 miles, track targets moving up to 600 miles per hour, and maintain lock through violent evasive maneuvers. The M9 could calculate firing solutions for targets at any altitude and any aspect angle, accounting for wind, temperature, and even the rotation of the Earth for long-range engagements. Most impressively, the system could track ground vehicles and even individual soldiers at shorter ranges, suggesting applications far beyond anti-aircraft fire. But the true test would come in combat, where enemy jamming, mechanical reliability, and the stress of battle would determine whether the system's theoretical capabilities translated to operational effectiveness. The answer came at Anzio, in the darkness of February 24, 1944, when Hauptmann Schneider and his formation encountered precision they could not comprehend. February 1944, Anzio beachhead. The tactical situation had deteriorated steadily for 3 weeks. German forces had contained the Allied landing, preventing any breakout toward Rome. The Luftwaffe controlled the night sky, conducting bombing raids with minimal interference. The American SCR-268 radars were being successfully jammed by German electronic countermeasures equipment. German bombers would approach, Their jamming systems would flood the radar frequencies with noise, and the anti-aircraft guns would fire blindly, wasting ammunition, while the bombers struck their targets with increasing confidence. 2 SCR-584 systems were rushed to the beachhead on February 23, transported by LST directly to Anzio Harbour. Technical teams worked through the night installing the equipment, running cables to nearby 90mm gun batteries, and conducting hasty checkout procedures. There was no time for extensive testing or crew training. The system simply had to work immediately, or the Luftwaffe would continue its devastating attacks. On the evening of February 24th, as 12 Junkers Ju-88s approached from the northeast, the SCR-584 operators detected them at maximum range. The automatic tracking system locked onto the formation leader. The M9 director calculated firing solutions continuously as the targets closed. At effective range, the command was given to engage. 4 90mm guns opened fire in rapid sequence, each shell guided by calculations updated hundreds of times per second. The German jamming equipment was completely irrelevant. The SCR-584 operated at frequencies the jamming systems could not reach, using microwave energy far above the bands where German electronic warfare equipment functioned. The conical scanning automatic tracking meant the radar operators did not need to see the targets on a display. The system tracked autonomously, immune to the noise and interference that blinded previous radar generations. Within 90 seconds, 5 German bombers were destroyed. The remaining aircraft scattered, breaking formation and fleeing north. The Luftwaffe did not return in force for over a week. When they did, additional SCR-584 systems were operational. The results were similar. German bombers that approached the beachhead were engaged at extreme range with accuracy that made survival a matter of luck rather than skill. By early March 1944, Luftwaffe Command had issued orders restricting operations near Anzio to cases of extreme military necessity. The air threat that had paralyzed the Allied beachhead was effectively eliminated. The success at Anzio was not simply about one engagement or one weapon system. It represented proof that electronic fire control had matured to the point where it could decisively affect combat outcomes. German technical intelligence immediately recognized the implications and began desperate efforts to capture and examine the new American radar systems. March 1944, Sicily, Technical Testing Station 27. Oberingenieur Franz Müller supervised the careful dismantling of an SCR-584 radar set that had been captured during Allied raids on Sicily. The system had been damaged by artillery fire, but large sections remained intact, including the antenna assembly, portions of the receiver, and most critically, several cavity magnetron tubes. Müller's team photographed every component, measured every dimension, and attempted to understand the engineering principles that allowed this system to function with such devastating effectiveness. What they discovered confirmed their worst fears about American technical and industrial capabilities. The cavity magnetron was manufactured to tolerances that German industry could not match in mass production. The antenna assembly used materials and construction techniques that suggested access to resources and machining capacity far beyond anything available in the Reich. The servo motors that drove the automatic tracking system were precision instruments that would require months of development to duplicate. Most disturbing was the complete integration of the system. Every component was designed from the start for mass production, with standardized interfaces, modular construction, and foolproof assembly procedures. The Americans had not created a prototype or limited production device. They had created a weapon system that could be manufactured by the thousands using semi-skilled labor in converted automotive factories. Müller's report to Wehrmacht High Command in late March 1944 was devastating in its conclusions. The SCR-584 represented American industrial and technological supremacy in electronic warfare. Germany possessed no equivalent system and lacked the industrial capacity to develop one before the war's conclusion. The automatic tracking capability alone would require years of development, and even if German engineers solved the technical problems, the magnetron production bottleneck would prevent deployment at meaningful scale. The report estimated that capturing and reverse engineering an SCR-584 would require at least 18 months of intensive development work, followed by at least 12 months of production preparation. By the time German forces could deploy equivalent systems, the war would almost certainly be decided by other factors. The recommendation was that Germany focus defensive efforts on systems that could be fielded quickly using existing industrial capacity, accepting that electronic warfare superiority had passed permanently to the Allies. But the SCR-584's impact extended far beyond anti-aircraft defense. American forces quickly discovered that the radar's precision and automatic tracking made it valuable for multiple applications that the original designers had never anticipated. The system could track artillery shells in flight, allowing ballistic corrections to be calculated based on actual trajectory data rather than theoretical calculations. This dramatically improved the accuracy of long-range artillery fire. The radar could detect vehicle movements at ranges exceeding 20 kilometers, providing early warning of German armor concentrations. Forward air controllers used SCR-584 systems to guide fighter bombers to ground targets with unprecedented precision, even in poor weather conditions that would have made visual bombing impossible. Most remarkably, the radar could track friendly artillery shells and hostile incoming rounds simultaneously, allowing counter-battery fire to be directed with accuracy that German gunners found inexplicable. German batteries would fire a single ranging shot to adjust their aim, and within minutes, American artillery would destroy their position using coordinates calculated from the shell's trajectory detected by SCR-584 radar. This application turned the traditional artillery duel completely on its head, making any German gun that fired more than a few rounds subject to nearly instant destruction. By May 1944, the SCR-584 had proven itself in every role its designers intended, and several they had never imagined. Production continued at 15 systems per day from Chrysler's Dodge plant in Detroit. The United States Army had received over 1,300 complete systems. The British Army had requested and received dozens more, designated the AA No. 3 Mark V in British service. Training programs at Fort Monroe and other installations were producing crews who could set up and operate the system within hours of arrival in a combat zone. The radar had become standard equipment for American anti-aircraft battalions. But the system's most dramatic test was still to come, against a weapon that would validate everything the SCR-584 represented about the revolution in electronic fire control. June 13, 1944, London, England. At 4:07 in the morning, air raid sirens wailed across northeast London. Civil defense crews watched in disbelief as a small aircraft streaked across the sky at extraordinary speed, its engine producing a distinctive buzzing sound. Anti-aircraft batteries fired, but the target was too fast, too small, and flying too erratically for traditional gun-laying methods to track effectively. The aircraft's engine suddenly cut out over Hackney. The machine fell from the sky and exploded in a massive fireball. 6 people died in the blast. This was the first Vergeltungswaffe 1, the V-1 flying bomb, Hitler's first vengeance weapon deployed against Britain. The V-1 represented a new kind of threat. It was essentially a pilotless aircraft, 27 feet long, with a simple pulse jet engine that gave it a top speed exceeding 350 miles per hour. A gyroscopic autopilot maintained heading and altitude. A simple propeller-driven mechanical counter tracked distance travelled. When the counter reached a preset value, the fuel supply was cut and the bomb fell to its target. The weapon was crude, inaccurate, and terrifying. Over the following weeks, German forces launched thousands of V-1s from sites in occupied France. The bombs fell randomly across London and southern England, killing over 6,000 people and injuring more than 18,000. The psychological impact was devastating. Unlike manned bombers that could be deterred or destroyed, the flying bombs kept coming day and night in an endless stream. Traditional air defences struggled against the V-1's combination of small size, high speed, and low altitude. Fighter aircraft could intercept them, but this required standing patrols that consumed fuel and limited the fighters' availability for other missions. Anti-aircraft guns fired thousands of rounds with minimal effect. The SCR-268 radar could detect the flying bombs, but its limited accuracy and manual tracking requirements meant hit rates remained discouragingly low. By late June 1944, British authorities were desperate for more effective countermeasures. The V1 campaign threatened to undermine civilian morale and divert military resources from the ongoing Normandy campaign. Prime Minister Winston Churchill personally requested that American forces share their proximity fuse technology for use over British territory. The proximity fuse, designated VT for variable time, was another revolutionary weapon developed through the National Defense Research Committee's programs. Work had begun in 1940 under Section T at the Applied Physics Laboratory of Johns Hopkins University, directed by Dr. Merle Tuve. The challenge was creating a miniature radio transmitter and receiver that could survive being fired from a cannon, operate reliably in flight, and detonate a shell when it approached within lethal distance of an aircraft. The device was astonishingly complex for something that would be destroyed seconds after activation. Inside a metal cylinder, 3 inches in diameter and 6 inches long, was a complete radio system. A battery activated by centrifugal force from the shell's rotation powered a vacuum tube oscillator that transmitted a continuous radio signal. When the signal reflected from a nearby target, the frequency shifted slightly due to the Doppler effect. When this frequency shift exceeded a predetermined threshold, indicating the target was within approximately 70 feet, the fuse fired a detonator that exploded the shell. Development required solving problems that initially seemed insurmountable. Vacuum tubes needed to survive accelerations exceeding 20,000 times gravity when the shell was fired. Battery electrolyte had to remain liquid at high altitudes, where temperatures dropped to -40 degrees. The entire system needed to cost less than $50 per unit, despite containing precision electronics that would have cost hundreds of dollars as laboratory equipment. By 1943, American industry was producing proximity fuses in massive quantities. Sylvania Electric Products operated factories in Pennsylvania and Massachusetts, where thousands of women, working under extraordinary secrecy, assembled the delicate components by hand. Crosley Corporation in Cincinnati employed over 10,000 workers producing proximity fuses. By 1944, production exceeded 70,000 fuses daily. Total wartime production would reach over 22 million units. The proximity fuse transformed anti-aircraft effectiveness. United States Navy ships that had required thousands of rounds to destroy a single aircraft with timed fuses now needed only a few hundred rounds with proximity fuses. The improvement was dramatic enough that American military authorities initially restricted the fuse's use to over water, where unexploded examples could not fall into enemy hands. The Germans were known to be working on similar technology, and American planners feared that captured fuses might accelerate German development. But the V1 crisis forced a reconsideration. The flying bombs followed predictable straight and level flight paths at relatively low altitudes. They were nearly ideal targets for radar-controlled anti-aircraft fire equipped with proximity fuses. Churchill argued that any unexploded fuses would fall into the English Channel or on British soil, not enemy territory. The risk of technology compromise was acceptable, given the urgent need for more effective defenses. In July 1944, American authorities released proximity-fused 90mm ammunition for use against the V1 threat. 20 SCR-584 radar systems were rushed to the English Channel coast and positioned in a defensive belt along the most common V1 approach routes. The British provided 80 QF 3.7-inch anti-aircraft guns, 94mm in diameter, to be controlled by the American radar and fire control systems. Each battery consisted of 8 guns, 1 SCR-584 radar, 1 M9 or British M10 director, and the necessary power generators and control equipment. The results exceeded even optimistic expectations. In the first week of operations, the gun batteries destroyed 17% of all flying bombs that entered the coastal defense belt. This was already better than previous methods achieved, but it was just the beginning. As crews gained experience with the equipment and refined their procedures, performance improved dramatically. By August 23, 1944, the batteries were destroying 60% of all V1s that entered the gun belt. By the end of August, effectiveness reached 74%. On one extraordinary day, the batteries shot down 82% of all flying bombs that approached. The improvement in ammunition consumption was equally dramatic. Early in the V1 campaign, British anti-aircraft batteries had fired an average of 2,800 shells to destroy a single flying bomb. With the SCR-584, M9 director, and proximity fuses working together, the average dropped to 156 shells per kill. In some cases, American 90mm batteries destroyed flying bombs with as few as 8 shots. The complete system, SCR-584 radar tracking automatically, M9 director calculating firing solutions continuously, 90mm guns adjusting aim in real time, and proximity-fused shells detonating at optimal distance represented the full realization of electronic fire control. Human operators monitored the system, authorized engagement, and handled exceptions, but the actual tracking, computation, and firing were automated to a degree that would have seemed impossible just 4 years earlier. British Home Guard units watching American batteries operate were astonished by the efficiency. They had become accustomed to firing thousands of rounds at V1s, with minimal effect. Watching American crews set up an SCR-584, detect an incoming flying bomb, lock the radar in automatic track, and destroy the target with a handful of shells seemed almost magical. When British officers asked American battery commanders how they achieved such remarkable accuracy, some Americans jokingly credited their Tennessee marksmanship heritage rather than reveal classified fire control technology. The V1 defensive success had strategic implications beyond the immediate protection of London. The flying bomb campaign was costing Germany significant resources, including launching sites, maintenance personnel, and the bombs themselves, at approximately 5,000 Reichsmarks each. If the defensive systems could destroy 70 to 80% of the bombs, the cost-effectiveness calculation shifted dramatically in favor of the defenders. More importantly, the demonstrated capability of SCR-584 systems against fast-moving aerial targets proved that the technology worked under the most demanding combat conditions. German technical intelligence recognized this immediately. August 1944. Wehrmacht Technical Intelligence Facility, Northern France. Oberingenieur Franz Müller received fragments of what German scouts identified as a new type of American anti-aircraft shell recovered from the English Channel. The fragments were unusual. Mixed with the standard steel casing and high explosive residue were components that should not exist in an anti-aircraft shell. Small vacuum tubes, copper wire wound into precise coils, capacitors, and what appeared to be a battery mechanism. Müller spent 3 days examining the fragments under magnification, photographing every component, and attempting to reconstruct the device's function. His conclusion was both brilliant and terrifying. The Americans had developed a proximity fuse that used radio transmission to detect targets and detonate shells automatically at optimal distance. The implications were staggering. The device represented a level of miniaturization, reliability, and mass production that German industry could not match. Each fuse contained a complete radio transmitter and receiver small enough to fit inside a shell, rugged enough to survive being fired from a cannon, and cheap enough to be expended by the thousands. Müller's report to Wehrmacht High Command in September 1944 was devastating. The proximity fuse, combined with the automatic tracking radar systems the Allies had deployed, created a fire control capability that made traditional air attack prohibitively expensive. Any aircraft or missile that approached Allied positions equipped with these systems faced destruction rates exceeding 50%. No air force could sustain such losses. The report estimated that Germany would need at least 2 years of intensive development to create equivalent technology, followed by at least 18 months of production preparation. Even then, German industry lacked the electronics manufacturing capacity to produce proximity fuses in militarily significant quantities. American factories were producing tens of thousands of fuses daily. Germany could not match even 10% of that output without completely restructuring the electronics industry. More critically, the proximity fuse represented only one component of a complete system. The SCR-584 radar provided automatic tracking with precision that German radar could not match. The M9 Director performed ballistic calculations continuously using electronic analog computation that German mechanical computers could not replicate. The entire system was designed from the start for mass production, modular replacement, and operation by minimally trained crews. German equivalents, where they existed at all, required skilled operators, constant maintenance, and hand adjustment to function reliably. By late 1944, captured American equipment told a consistent story. Every radar, every radio, every fire control system demonstrated industrial and technological superiority that Germany could not overcome. The gap was not simply in individual devices, but in the complete industrial infrastructure that produced them. American electronics factories employed hundreds of thousands of workers, mostly women, operating specialized machinery that stamped, wound, assembled, and tested components automatically. Statistical process control ensured quality without individual inspection. Standardized parts allowed interchangeability without custom fitting. The entire production system was designed for scale in ways that German craftsmanship-oriented manufacturing could never match. December 1944. Battle of the Bulge, Ardennes Forest. The proximity fuse demonstrated its effectiveness in an entirely different role. When German forces launched their surprise offensive through the Ardennes in December 1944, American artillery batteries responded, with proximity-fused shells that exploded in airbursts above German infantry positions. The effect was devastating. Traditional artillery shells exploded on contact with the ground, sending shrapnel upward and outward in a cone. Soldiers could survive by taking cover in foxholes, behind vehicles, or in buildings. Proximity-fused shells exploded 20 to 70 feet above the ground, depending on caliber, sending shrapnel downward and outward in a pattern that covered far more area and made cover largely ineffective. German soldiers caught in the open by American artillery barrages equipped with proximity fuses suffered casualty rates that exceeded anything they had experienced from traditional artillery. One American battalion concentration caught a German battalion attempting to cross the Sauer River and killed 702 soldiers by actual count. The German survivors reported that the shells exploded above them in patterns that made escape impossible. General George Patton wrote to the War Department describing the proximity-fused shells as devastating and stating that when all armies possessed this technology, entirely new methods of warfare would need to be devised. German forces had felt safe from timed artillery fire during the Ardennes offensive because the terrible weather prevented accurate aerial observation needed to adjust fire. The proximity fuse made observation unnecessary. American artillery could fire for effect immediately, with shells exploding at optimal height automatically. By January 1945, the combination of SCR-584 fire control radar and proximity-fused ammunition had demonstrated effectiveness in every role tested. Anti-aircraft defense, counter-battery fire, artillery support, and even vehicle detection. The technology had transformed from experimental systems in 1942 to decisive weapons that fundamentally changed how ground and air combat functioned. Production numbers tell the story. American industrial commitment. Between 1943 and 1945, Chrysler Corporation produced 2,098 complete SCR-584 systems. Additional production came from other manufacturers for specialized variants. Over 22 million proximity fuses were produced by multiple factories. The MIT Radiation Laboratory employed nearly 4,000 people at peak. Bell Laboratories committed hundreds of engineers to fire control development. The entire program represented an investment of billions of dollars in current terms and engaged a significant fraction of American electronics manufacturing capacity. Germany never came close to matching this effort. Despite developing over 30 different proximity fuse designs and multiple radar systems theoretically equivalent to Allied equipment, German industry never achieved mass production of any electronic fire control system. The reasons were complex but ultimately came down to industrial philosophy and manufacturing capacity. German engineering emphasized technical sophistication and individual quality over mass production. Skilled craftsmen built equipment using traditional machining methods. Each unit was individually tested and adjusted to achieve optimal performance. This produced excellent equipment in small quantities, but could not scale to the millions of units modern warfare demanded. American engineering emphasized design for manufacture, statistical quality control, and automation. Semi-skilled workers operated specialized machinery that produced components to specifications that eliminated the need for individual adjustment. This produced adequate equipment in unlimited quantities. Adequate equipment available in overwhelming numbers defeated excellent equipment available in limited quantities. The lesson was harsh but clear. May 8, 1945, Germany surrendered unconditionally to Allied forces. Among the equipment inventoried by occupation, authorities were extensive technical intelligence reports documenting German examinations of captured American radar, radio, and fire control systems. The reports were accurate, professionally done, and brutally honest about German inability to match American capabilities. Oberingenieur Franz Müller's final report, written in April 1945 as Soviet forces approached Berlin, concluded that Germany's defeat in the electronic war was inevitable. From the moment Allied forces deployed integrated fire control systems combining microwave radar, electronic computation, and proximity fuses. The individual components were impressive, but the real achievement was integration and mass production. Germany had competent scientists who understood the theory. Germany had skilled engineers who could build working prototypes. What Germany lacked was an industrial base capable of producing high-technology electronics in quantities that made strategic difference. Post-war analysis by American military historians confirmed that the SCR-584 and associated fire control systems significantly shortened World War II and saved thousands of Allied lives. The radar's effectiveness against V-1 flying bombs alone prevented tens of thousands of British civilian casualties. Its use in anti-aircraft defense protected Allied shipping, ground forces, and rear areas from air attack. Its application to counter-battery fire reduced Allied casualties from German artillery. Its role in the Battle of the Bulge helped blunt the last major German offensive. Estimates vary, but conservative calculations suggest that improved fire control technology, including the SCR-584, proximity fuses, and automatic tracking systems, shortened the war in Europe by 3 to 6 months. This translated to approximately 100,000 to 300,000 fewer military casualties and prevented continuation of the Holocaust for additional months. The technology's impact extended far beyond World War II. The SCR-584 remained in service with American and Allied forces through the 1950s. Modified versions were adapted for the Corporal missile system and other early guided weapons. The automatic tracking principles pioneered with conical scanning became standard in radar systems worldwide. The proximity fuse concept evolved into the guidance systems for surface-to-air missiles that replaced anti-aircraft guns in the Cold War. The M9 Director represented an early example of analog electronic computation applied to real-time control problems. Its principles influenced the development of fire control computers for ships, aircraft, and eventually guided missiles. The same engineers who designed the M9 went on to develop more sophisticated computational systems that culminated in digital fire control computers by the 1960s. But perhaps the most important legacy was proving that integrated electronic systems could decisively affect combat outcomes. The SCR-584 was not simply a better radar, it was a complete weapon system that combined detection, tracking, computation, and fire control into an automated process that required minimal human intervention. This represented a fundamental shift in military technology from individual weapons to integrated systems. The shift influenced all subsequent military development. Modern warfare is defined by networked sensors, automated computation, and precision guidance. The principles visible in the SCR-584, automatic detection, continuous tracking, real-time calculation, and immediate response, are now fundamental to every military system, from artillery to aircraft carriers to satellite networks. In 1999, the Smithsonian Institution opened an exhibit featuring an SCR-584 radar set, serial number matching one of the units deployed to Anzio in February 1944. The radar had been recovered from storage and restored to display condition. Beside it, the exhibit displayed German technical intelligence reports documenting the examination of captured American equipment. Visitors could read Oberingenieur Müller's observations about automatic tracking, integrated fire control, and mass production techniques that Germany could not match. The exhibit made clear that German technical experts understood exactly what they faced and reported accurately to their superiors about the implications. The exhibit also displayed an M9 gun director and a cutaway proximity fuse, showing the miniature radio components. Educational materials explained how the three technologies combined to create a weapon system that fundamentally changed anti-aircraft warfare. The curator's notes emphasized that the achievement was not any single invention, but rather the integration of multiple technologies and the industrial capacity to produce them at scale. The story of the SCR-584 demonstrates that technological superiority in modern warfare requires more than brilliant individual inventions. It requires industrial capacity to manufacture complex equipment in massive quantities, organizational ability to integrate multiple technologies into functioning systems, and the resources to sustain production throughout extended conflicts. Germany had brilliant scientists and skilled engineers, but Germany lacked the industrial infrastructure to compete with American electronics manufacturing, operating at full capacity. The contest was decided not in laboratories or proving grounds, but in factories producing thousands of precision radar sets, millions of vacuum tubes, and tens of millions of proximity fuses. The electrician Percy Spencer, who solved the magnetron production problem, never worked directly on the SCR-584, but his manufacturing breakthrough enabled Raytheon to supply the cavity magnetrons that powered every SCR-584 radar. Without Spencer's innovations, the radar would have remained limited by magnetron scarcity. The contribution was indirect but essential. This pattern repeated throughout the American war effort. Individual achievements mattered, but the real advantage was systematic. The nation that could design for mass production, organize factories efficiently, train workers rapidly, and sustain output for years would ultimately prevail. The SCR-584, together with its associated fire control systems, represented American industrial capacity applied to electronic warfare with unprecedented effectiveness. The result was a weapon system so effective that German engineers examining captured examples concluded the electronic war was already lost. The mathematics were brutally clear. When radar tracked automatically, when computers calculated continuously, and when proximity fuses detonated optimally, the defensive advantage shifted so decisively that no amount of tactical innovation could compensate. Hauptmann Erich Schneider survived his encounter with SCR-584 controlled anti-aircraft fire at Anzio in February 1944. He flew 5 more missions over Allied-controlled territory before being shot down by American fighters in March. He spent the remainder of the war in a prisoner camp in North Africa, then Italy, finally returning to Germany in 1946. In interviews decades later, he described the night of February 24th as the moment he realized Germany would lose the war. The precision of the anti-aircraft fire, the way it tracked through every evasive maneuver, the apparent ability of the gunners to predict exactly where his aircraft would be, seconds in advance, all suggested technology that Germany could not match. He had been trained to believe that German engineering was superior, that Allied equipment was crude and mass-produced, that skill and determination would overcome material disadvantages. One night of flying through SCR-584 directed fire destroyed those assumptions completely. The shells appeared exactly where his aircraft would be, not where it was. The system was predicting the future and placing high explosive in that predicted position with accuracy that made survival a matter of chance. No amount of pilot skill could evade weapons that anticipated every maneuver. Schneider's realization, shared by thousands of German soldiers, sailors, and airmen who encountered American technology in the final years of the war, was simple and devastating. Germany was fighting an industrial power that could produce in a day what Germany produced in a month. The technological gap was not simply about better equipment, it was about fundamentally different approaches to manufacturing, different philosophies about how technology should be designed, and different capabilities for sustaining production at scale. The story of how German engineers examined American radar equipment and realized the war was already lost is ultimately a story about industrial capacity determining military outcomes in modern warfare. The SCR-584 was an extraordinary technical achievement, but its real significance was that America could build thousands of them, while Germany struggled to build dozens of equivalent systems. That disparity, repeated across every category of military equipment from radios to radar to proximity fuses, made defeat inevitable. The lesson remains relevant today. In an age of hypersonic missiles, stealth aircraft, and cyber warfare, the fundamental truth endures. The nation, with greater industrial capacity to produce high-technology equipment in overwhelming quantities, to sustain production through extended conflicts, and to continuously improve systems based on operational experience, holds decisive advantage. Technology matters, but production capacity determines outcomes. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this.